Okay, so we're starting chapter 7, which is all about estimating like population parameters. So there's 3 sections. The first one's focusing on proportions, which is like percentages of something occurring. Like there's a 50-50 chance of flipping a head compared to a tail when I flip a coin. So we're all about population parameters. And this is important because the last 6 chapters have been working with samples. And it's easy to like collect a sample of 100 people and asking them everybody the same question. But with a population, I want to ask everybody involved. So if I'm asking about like, do you know what Facebook is? I want to ask everybody in the world, and that's literally impossible to do. So we're going to use samples to basically estimate what a population could be. And we have to make sure we have good sound statistics because we have to make sure our sample is good enough to estimate the population. If our sample is bad, there's no way that it can estimate a population parameter. So that's what this whole chapter is about. To start, we have to define these 3 things because they're going to be used in this whole chapter, all 3 sections. A point estimate. This is a single value, used to estimate a population parameter. So this is what we'll trying to be finding, or it'll be given to us as our sample statistic basically. We're going to use that to estimate a population parameter, but we can't like say with exact certainty that that's what the population parameter actually is. And that's why we have what is called a confidence interval, and this is sometimes abbreviated CI. So I can't say like, oh, it is exactly 50% chance of flipping a head, which we already know that. It is what it is. Where I can't say, oh, 70% of people know what Facebook is. I can instead give like a range. Maybe I'm confident that 60 to 80% of people know what Facebook is. And that's more legitimate than saying, oh, exactly 70%. So that's what we're getting to. So I'm going to say this is a range of values used to identify the location of the population parameter. But if I'm saying, oh, well, 60 to 80% of people know what Facebook is, am I 80% confident that's accurate? Am I 90% confident that's accurate? Am I 95% confident? Like, I need to know how confident I actually am in the range of values that I'm actually stating. So that's what the confidence level is. This is the percentage, which they identify as 1 minus alpha. And remember, alpha is talking about the area, so we'll connect it back to a normal distribution. The percentage of confidence that the population parameter lies in the confidence interval. Yeah. So we're going to need to understand these 3 things. So we're doing a population parameter or population proportion today. So we want to figure out how can I actually construct this confidence interval with proportions. So there's 5 steps that we have to go through. We have to check the requirements, even make sure that I can calculate a population proportion to begin with. So our first requirement is knowing that it's a simple random sample. And remember this first chapter, we talked about all the ways that I could conduct a sample. A simple random sample is like the golden nugget. This is what I want to try and do every single time. But this is sometimes complicated to do because I need to like label every single person and then randomly select like a number that corresponds to that person. There are other samples like voluntary response sample and convenience sample and stratified sample, all those fun words that we talked about, but we're trying to go for a random sample. Our second requirement has to satisfy the binomial probability requirements. And this was tying back to chapter 5. So remember, binomial is like two things, and I think there was 4 requirements for a binomial probability. I do remember one of them. I have to have 2 outcomes, so either, like my example, they know what Facebook is or they don't know what Facebook is. Like those are your 2 outcomes that could possibly happen for a proportion is what we're talking about. I know each event has to be independent. So one person's response doesn't affect another person's response. I want to say like they're all equally likely. So like each response is equally likely to occur with each person. Oh boy. And I want to say it's like the probability sum to 1. Like if there's 60% chance you know what Facebook is, then there has to be a 40% chance that I don't know what Facebook is. So it has to sum up to 1. I think those are the 4 requirements. I could be wrong. The main one is having 2 outcomes, basically. Okay, our third requirement, there are 3. I need at least 5 successes and 5 failures. So I need to know, in whatever sample I'm doing, 5 people know what Facebook is, and at least 5 people don't know what Facebook is for us to even construct this proportion. Okay, so once we have satisfied all our requirements, we have to find the critical value so that way we can calculate the margin of error. So this actually reads, it's Z, and then it's alpha over 2. So that's the whole subscript. It's not A over 2, it's alpha over 2, so alpha represents the area. We have found critical values before. Critical values are like the endpoints on a normal distribution graph. So in this case, they're saying that the area to the left and the area to the right, both of these together equal alpha, which is the area. But since it's talking about alpha over 2, like this specific point, this is half the area on the left side, half the area on the right side. And I want to find this specific z-score on both ends. Remember, z always represents z-score. There is a way to actually calculate the z-score in our graphing calculator. We'll cross that bridge when we come to it. There is a table that we will fill out because our first example is about calculating a z-score and a critical value, just to refresh our memory. We use the same confidence level for many problems, so we're just going to make a table so that way we can reference it. We don't actually have to draw our normal distribution graph every single time to get the same z-score every single time. So we'll come back to finishing number 2 here. Our formula for the margin of error, so basically this is how far off our statistic value is. So if I found a statistic that 70% of people know what Facebook is, I know that's not exactly the population proportion. I should be off by some percentage point. So this is what our margin of error actually is. Like, how far off am I with my sample? And so to calculate, this is taking our critical value and we're multiplying it by the square root of p hat times q hat over n. And just to note, p hat, this is our sample proportion. And maybe I'll say like success, because q hat is our sample proportion failure. And then n is our sample size. So if I found my sample statistic to be 70% of people know Facebook, then our failure is 30% of people don't know what Facebook is. So that's why we have to have 2 outcomes, so I satisfy p hat and q hat. Once I have the margin of error, I can actually construct our confidence interval, because if I know how far off I am, I can add that value to my sample statistic and subtract that value from our sample statistic. So I want to estimate P, which is our population proportion. I know this proportion value has to be less than our sample proportion plus our margin of error. And it has to be greater than our sample proportion minus our margin of error. So I'm going to add the margin of error and subtract the margin of error from our sample proportion to estimate regular P, which is our population proportion. Remember whenever they do those like symbols, those are always talking about sample statistic. Whenever they do Greek letters or just regular letters, they're always populations. One key little tip there. Okay, and then just step 5, we're always rounding to 3 significant digits. That was always with probabilities. That carries forth with estimating population parameters. Okay, so we're going to calculate the critical value, Z alpha over 2, corresponding to the 90%, 95%, and 99% confidence level. And those are like the 3 main ones that we use consistently. And then we're going to fill in our solutions under step 2 here. So just to sum up, this always comes from a normal distribution graph. And let's talk about 90% first. So basically, if I want a 90% confidence level, this is talking about the area under a curve. And remember, the area under a normal distribution graph is always equal to 100% or one whole value, if I wrote it as a decimal. So this tells me that 90% should fall in the middle, which then means there's 10% left out for the edges. So this edge here and this edge here, they both add up to be 10% total, or 0.1. But if I split it in 2, then half of 10% is 0.5. So this area is 0.05, and this area is also 0.05. So then hopefully we remember from the last test, I want to actually calculate these z-scores. And to do that on our graphing calculator, we use inverse norm to figure those out. Okay. So inverse norm, if I'm finding the left z-score, then my area is 0.05, because remember, inverse norm is always area to the left. So 0.05, you could just leave mean and standard deviation as 0 and 1. I got a z-score for this as 1.64. If I'm calculating the z-score on the right tail, same thing, I want the area to the left. So the area to the left is everything over here. So it's basically 1 minus 0.05, so 0.95. So if I type in 0.95 as my area, I get a z-score of 1.64. And remember, z-scores, we always round to 2 decimal places. So in your table, for a 90% confidence level, we have a z-score of 1.64, is what we just calculated. And so you might have to go back up to step 2, where we were talking about z-scores. So I'm going to find 95% and 99%. So basically, I just want to redo all of this. So our areas are the only thing that change here. So if we do the 95%, oh snap. So same thing, I have a left tail and I have a right tail. So both areas combined are 5%, but I split them in half because I have 2 tails. So that means this area is 0.025. This area is 0.025. And we want to calculate the z-scores here. Okay. I got out negative 1.96, and I believe this one would be 1.96. We always want to work with the positive z-score. Okay, you could do the next one by yourself, but I'm just going to write down the next one. 99% confidence level, I get a critical value of 2.58. Okay, so we're going to use these to actually construct a population parameter confidence interval. Whew. All right. So in the Pew Research Center poll of 1,007 randomly selected adults, it showed that 85% of respondents know what Twitter is. Woo. Okay, so I have to check our requirements. So this is going to guide us through all 5 steps here. So requirement number 1, is it a simple random sample? And we should say yes, because it said randomly selected adults. So satisfied. Step number 2, a binomial probability distribution. So as there are two outcomes, we should say yes, because either they know what Twitter is or they don't know what Twitter is. And then each person's response is independent of each other. Satisfied. Step number 3, are there at least 5 successes and 5 failures? So are there at least 5 people that know what Twitter is and 5 people that don't know what Twitter is? So if I was actually going to do this, I'd have to find 85% of 1,007 to figure out how many people know what Twitter is. So if I multiplied 0.85 times 1,007, I get out there's 856 people that know what Twitter is. So then that would mean there's 151 people that don't know what Twitter is. Because if I did 1,007 minus 856, I get 151. So I have at least 5 people, so those are over 5. So we are satisfied. So this means I can go forth and calculate a population parameter confidence interval. Whew. Okay, so let's find the margin of error that corresponds to a 95% confidence interval. So I want to calculate our e-value. So it always starts with our critical value, and we always define our critical value based on our confidence interval or confidence level. So since it's 95, I can go back up. That means I'm using 1.96 as my critical value. And then I'm multiplying by the square root of our sample proportion value. So 85% is our success value, our p-hat, but I need to write it as a decimal, so 0.85. But then I want to multiply by our proportion of failures, so our percentage of people that don't know what Twitter is. So that's 0.15. P-hat and Q-hat should always sum to be 100% because I either have one outcome or the other. And then I'm dividing it by my sample size, which is 1,007. So if we would type this into our calculator, I got out 0.022, and then I'll do 1, so that way I have 3 significant digits there. Part C, so that was step 2. Step 3, I want to actually construct our interval. So our sample proportion, so our p-hat value was 85%. So I want to add our margin of error to 0.85, and I want to subtract our margin of error to 0.85. So if I'm writing my inequality statement, I have 0.85 plus our margin of error, and then I have 0.85 minus our margin of error, just to get a range of values here. So doing that, so on the left side, I have 0.82, and then I'm going to round to 8. So I have 3 significant digits. And then the other side, I get 0.872. So basically what this is saying, I'm confident that between 82.8% and 87.2% of people know what Twitter is. I still have like 15 minutes of this video to make here. Yeah. Okay. So interpreting our answer, there's a set way of knowing how to write this. So we would say we have a 95% confidence that the population parameter lies within 82.8% and 87.2%. Okay, so then part D, based on the results, can we safely conclude that more than 75% of adults know what Twitter is? So since it's more than 75% and our sample population proportion, they're both larger than 75%, we would say yes, because population proportion is larger than 75%. Are you guys wanting to take your test? Okay. This video is going to be nightmare. This is my second time making this, so I'm not stopping.
Okay, so that's fine. Go for it.
So here's,
Maybe I should move. Where did the first period people say? I'll talk. I just want to get this.
okay, I'm still making this video. It's a disaster. Okay, yeah. So part E, assuming that you are a newspaper reporter, write a brief statement that accurately describes the results, includes all of the relevant information. So you'd say, basically our statement from above, we are 95% confident that our population parameter of people knowing what Twitter is lies within 82.8% and 87.2%. I'm not going to write that down, but that's what we would say. Okay, so there's a correct way to interpret confidence intervals, and there's an incorrect way of interpreting confidence intervals. We have to make sure we do it the correct way. This is our statement that we'll use all the time, so we just have to know what this is. Sometimes we're going to talk about mean, so like this value would change. Instead of saying population proportion, we could say population mean. And then whatever we actually calculate is going to change as well. So this is just our standard way of saying it. Because our incorrect way, so it says there's a 95% chance that the true value of P will fall between those two values. So we can't really say 95% chance because that's not what it's actually saying. We're 95% confident that it's going to fall. So you can't make it like a probability statement when you're talking about population proportions. The other one, 95% of sample proportions will fall between 0.405 and 0.455. So basically you're, once again, saying this is like a probability. There's a 95% chance that it'll fall between here. Same thing, we can't assume that if we did 95 chances that the next one would fail. Like that's kind of what you're saying, and that's not accurate. So it always has to be 95% confidence, not like probability-wise. Okay, let's do another one. So suppose we want to know the true proportion of Nebraskans who watched the Big 12 title game in December of 2010. A survey conducted by the Lincoln Journal-Star reports that 993 out of 1,358 people surveyed had watched the football game. What can we say about P? So we're going to compute the 95% confidence interval. Okay, so step one, check requirements. So is it a random sample? Basically, we know it's a survey conducted by the Lincoln Journal-Star. I would probably say that's not a simple random sample, but we're going to carry forth. We have to satisfy the binomial probability requirements. So are there two outcomes involved? Yes, because either you watched the game or you didn't watch the game. And then requirement number 3, do we have at least 5 successes and 5 failures? So did at least 5 people watch the game and at least 5 people not watch the game? Definitely yes, because 993 people watched the game and like 400 people didn't. So those are all satisfied. Step number 2, we want to find our critical value, which since it's a 95% confidence interval, our critical value is 1.96. Step number 3, we want to calculate the margin of error. So using our critical value, we're multiplying it by the square root. So I need to actually figure out what P hat is here and Q hat. So P hat is our sample proportion. So what's the percentage of people that actually watched the game? So I know 993 people watched it out of 1,358. So we need to divide that. I got 0.731, and I'll round to 3. So that would mean I have 0.269 left over for people that didn't watch the game. So using those in our formula. And we're divided by your sample size, which we surveyed. 1,358 people. Okay. Type in our calculator. Oh, jeepers. I got 0.0236, still rounding to 3 significant values. Okay, step 4, I want to actually construct my confidence interval. So our p-value, I have to add it, our margin of error, to our sample proportion. So the 0.731 plus 0.0236 and the 0.731 minus 0.0236. Okay, and I just failed, so I didn't round to 3 digits. Great. So this is what we actually should be writing down instead. Okay, but if I was like interpreting this, I would say we are 95% confident that the true value of the population proportion lies within. And you can write it as a percentage if you want to, or the decimal, 0.707 and 0.755. So either 70% of people to 75% of people actually watch the game. We're confident that if I surveyed everybody in Nebraska, that percentage of people will watch the game. Okay, doing the same thing but with a 99% confidence interval. So I'm going to skip straight to step 3 with our margin of error. So if it's 99% confidence, that changes our critical value to 2.58. But our sample proportion and our sample failure stay the same. So our margin of error is going to change, our proportion confidence interval is going to change, and then we'll see the connection between the two. Because we want to know, is it better to be 99% confident or 95% confident? We shall see. Okay, so then if I make my inequality here, so I'm adding my margin of error to 0.731. Okay, and I got 0.762. And I could subtract my margin of error from our sample proportion. And I got 0.7. Okay. So same thing, I'd say like we are 99% confident that the true population proportion would lie between 0.7 and 0.762. So I want to actually plot both intervals on a number line so we can see how does a 95% confidence interval and a 99% confidence interval compare to each other. Okay, they're fairly the same. So I think I'm going to count by like hundredths. So like 0.7, 0.71, 0.72, and so on. Okay. So here is 95%. So we're at 0.707. So that's like here-ish. All the way to 0.7546. So this would be, what did I just say? 95% confident. And then 99%, so it'd be from here to here. Okay. So you should be asking ourselves, why is the 99% confident wider on our number line instead of the 95% confident? So basically, the more confident you are, the wider your interval, because you have to ensure that the population proportion actually lies between those two values. So if I did a 90% confidence interval, that would be smaller because I could be more accurate because I'm less confident in my value, basically. Hopefully that makes sense. Okay. Whew.